When you innovate, and it's writ large, you have grand epic adventures that echo through the educational pipeline. How might it do it? I stand up in front of an 8th grade class and I say, who wants to be an aerospace engineer? So that you can design a plane that's 10% more fuel efficient than the one your parents flew. That's one scenario. Who wants to be an aerospace engineer so that you can design an airplane that can navigate the rarefied atmosphere of Mars? I'm going to be getting the best students in the class. Not everybody cares about fuel efficiency. We want them to, but that's not how you get smart people to express their smarts.
About the difference between an astronomer and an astrophysicist.
Okay, there's no difference.
Oh, okay. Well.
Yeah, next question.
I knew that.
No, up until the 1860s or so, early 1850s, but really riding high 1860s and 1870s, the application of spectroscopy to the universe became a big business, big cottage industry. And what that meant was, when you're sitting behind a telescope, you could deduce more about the universe than where the star was in the sky and how bright it was. You could analyze the light with the spectroscope and determine the chemical composition of the star. You could look at the spectral features and check for Doppler shifts in those spectral features to judge, is the star moving towards you or away from you? If the spectral feature is broadened, that tells you that the star is spinning fast. Because it's one star unresolved, some part of the star is moving towards you, that gives you a little bit of a blue shift in the line. Some part is moving away from you, and there's a continuum of emissions in between. So the line actually fattens in the spectral signature. And so you can deduce the rotation rates, the speeds, and all of a sudden, laws of physics that were previously enjoyed in the laboratory were now cast into the universe. Laws of physics beyond simple gravity. Chemistry, for example. And, quantum mechanics, not yet invented, but of course, spectral lines is all about quantum mechanics. So in the late 1800s, departments of astronomy that were freshly conceived were then called departments of astrophysics. And the Journal of Astrophysics was born, predated by a Journal of Astronomy, but today we all do the same thing. We all have extensive training in physics and mathematics, and we all talk to each other completely fluently.
So you're mostly doing a combination of observational work, data collection, and analysis.
Yeah, that's right.
And computers.
And very few of us do it all. There are people who primarily go to telescopes, others who primarily are pencil and paper, and others who primarily are on a computer. And it's the synthesis of those that advances the frontier. Okay, it is true. We fear death because we are born knowing only life.
Right.
I get that. However, I take another view, because I've been asked, if you could live forever, would you?
Yes.
Okay, we're
Don't
done
even
with the
have to
interview.
finish the sentence.
Yes. No, okay, sure, that's an attractive idea. But the way I look at it is the knowledge that I'm going to die that creates the focus that I bring to being alive. The urgency of accomplishment, the need to express love now, not later. If we live forever, why ever even get out of bed in the morning? Because you always have tomorrow. That's not the kind of life I want to lead.
But why, don't you fear not being around?
I fear living a life where I could have accomplished something and didn't. That's what I fear. I don't fear death.
You don't fear the unknown?
I love the unknown. I love the, you know what I want on my tombstone? My sister has this in her notes, because in case I can't tell anyone after I die. On my tombstone, a quote from Horace Mann. great educator. Be ashamed to die until you have scored some victory for humanity. That's what I want on my tombstone. There was a day when the Bible was this, let's take Christianity just for simplicity here. The Bible was the source of people's spiritual enlightenment and the entire record for how the sun, moon, and stars and life got here. And so it was pretty much everything to everybody. Beginning in 1600, when the methods and tools of science became honed, primarily with the work of Galileo, there are some philosophers in there, Francis Bacon, helped to shape what it meant to think about the physical world and to deduce what is true and what is not about the physical world. Newton would come after Galileo. People started noticing that if you used the Bible to make statements about the physical world, you were getting the wrong answer. The tools of science was giving you a different answer. And Galileo was initially disturbed by this, and he was a religious man. He said to himself, well, he came up with a rather clever phrase. He concluded that the Bible tells you how to go to heaven, not how the heavens go. Because he was studying the movement of the planets in the sky. And so he came to a conclusion from his religious philosophy. How does he reconcile this? He said, God must have written two books. Scripture, where you learn how to understand God, and the book of nature, where you understand nature. And so from then onward, religious people began to think of the Bible not as a science textbook, but as a reference for spiritual enlightenment. And in this day, enlightened religious people are right in lockstep with that. And you might have seen even the Pope of the Catholic Church a week ago, 10 days ago, said publicly something that's already been in Catholic doctrine, at least since the middle of the 20th century, that science will tell us what it does, and that's a good thing. And from their point of view, it further glorifies God, whatever it is you discover. And they're not trying to match the discovery with some passage in the Bible. There are some people who can't even allow that to happen. That the Bible is, in fact, their source of science for the world. That's when you have a rift between science and religion. You don't otherwise have this rift. And so in the United States, we have they're called fundamentalist groups, where they are certain the Bible is correct in every way, and they want to put it in the science classroom. In a free country, in principle, you could do that. If you just vote it that way, in a free democracy, you can vote all of your textbooks to be completely infused with religious, all your science textbooks, to be completely infused with religious philosophy. You could do that. But I can tell you with certainty that that is not the region, the state, the country that's going to lead the world in anything scientific or technological, because they don't understand what science is and how and why it works. Not only that, how much does NASA get? I've done this experiment. I ask people, those that say, well, these people, okay? And so how much do you think NASA's getting? Here's your tax dollar. Pull out $1. Here's your tax dollar. How much are they getting? Okay? And here we go. Got my dollar. Oops, that's a 5. Wait a minute. Oops, that's another 5. There we go. Dollar. Tax dollar. How much? Here's your tax dollar. Is it 10 cents, 20 cents, 30 cents? How much is NASA getting? It is getting 1/2 of 1 penny of this tax dollar. 1/200th. That's not even, you're not even in the ink yet. Here, you're in the edge. That pays for the rovers, the space station, the space shuttles, the Hubble telescope, all the NASA centers, NASA headquarters, all of that. And I ask you, how much is the universe worth to you? If you look at the chemical ingredients of life itself,
You remember from biology class, we're mostly water. And good old water is H2O. 2 hydrogens, 1 oxygen. And if you could look at the sort of the element budget of life, hydrogen is number 1, as expressed in the water molecule. The number 2 in the human body is oxygen, turns out. Number 3 in the human body is carbon. 4 is nitrogen. 5, you find on all lists, is other. Okay, now if you go to the universe, that's the O on the periodic table. You didn't know that? That's not for oxygen, it's for other. So you go into the universe, number 1 ingredient in the universe is hydrogen. That was true in life. Number 2 ingredient in the universe is helium. We don't have that one.
Yeah, it doesn't like
but
anybody.
now, how come? Well, because helium is chemically inert. You can't do anything with it even if you wanted. You can inhale it, okay? And sound like Mickey Mouse, yes. Next in the universe is oxygen. Next, carbon. Next, other. Thank you, in the 3rd row there. So, actually that was the 2nd row. They must be related to the 2nd row here. We are 1-for-1 matchup with the most abundant ingredients in the universe. Of these, carbon is the most chemically fertile element in the entire periodic table. You can make more kinds of molecules with carbon than all other molecules combined. So, if you were going to experiment through the forces of nature with complex chemistry, and you had to pick an element to base it on, carbon is your man. Or your woman, however that goes. Okay, so what I'm saying is, given what carbon is capable of doing, perhaps we shouldn't be so surprised that there's life, because we are carbon-based life. We're just another one of the things carbon has rolled up its sleeve. Maybe life is inevitable, given the abundance of carbon and oxygen and nitrogen and hydrogen in the universe. Try to invert that view. Otherwise, you're left thinking, hey, we're special. You know I would give you right to say you're special? If life on Earth were made of an isotope of bismuth. That stuff is nowhere in the cosmos, and then we're made of it, we're special.
As you fall towards the center of a black hole, that difference in gravity grows.
Uh-oh.
Now,
I think I'm going to get elongated.
okay, so initially it kind of feels good. You know, you kind of stretch. Stretching feels good, right? We all want to stretch. When you wake up in the morning, you don't crunch, you stretch.
Yeah.
So it feels good, but then you realize that the growing force is unrelenting. And it will reach a point, you can calculate this, where the difference in gravity exceeds the molecular bonds that attach your flesh as one solid piece of body. And so there's a point where you'll snap into 2 pieces, and it'll likely be at the base of your spine. Now, those 2 pieces then begin to feel this difference in gravity between their top and their bottom, and then they snap into 2 pieces. So we go from 1 to 2 to 4 to 8 to 16 to 32. And eventually you become this stream of atoms headed down towards the abyss. Now, it's actually worse than that, because as you fall, we know from Einstein's general theory of relativity, which is our understanding of gravity, that the fabric of space and time funnels down to a point. So not only are you stretched head to toe, you are extruded through the fabric of space like toothpaste through a tube. December 2004, we discover an asteroid. We have a couple of data points on its position in the sky. You look at its speed, you get a Doppler shift on it. You get its direction, you plug it into the computer. There was some 20% chance it was going to hit Earth on April 13th, 2036. Did you hear about this asteroid when it was discovered? No, because that same week was the Indonesian tsunami.
that same week. And so rightly so, it did not lead the headlines the way the tsunami did. However, if you did the calculation, you would show that if it hit Earth in the center of the uncertainty range, it would hit the Pacific Ocean 500 kilometers west of Santa Monica. It would plunge into the ocean to a depth of 3 miles. It would explode at that depth, cavitating the ocean in a hole 3 miles wide. Now you have a wall of water 3 miles high. What happens to that wall of water? It just spills back into the hole that was just made, splashes into itself, and rises high again. That first impact creates a tsunami that's 5 stories tall. By the way, this asteroid is the size of the Rose Bowl. In other words, it would fit neatly in the Rose Bowl the way an egg does in an egg cup. So, So, here's the first wave. The first wave is just from that first impact. You cavitate the ocean, it fills up again, rises high into the stratosphere, falls back, cavitates the ocean again. Now it's water cavitating the ocean, not the asteroid. That sends another wave, and this repeats. Calculations show this will repeat about 40 times. 40 times. 40 tsunamis, one right after another. What's interesting to me is that tsunami would take out the entire west coast of the United States, do $10 trillion in damage. It would make the Indonesian tsunami look like a slightly overflooding puddle. So it was a lost opportunity to compare and contrast magnitudes of disaster. It would later make the news when better data became available. But let me explain this tsunami to you. So it's a wall of water 5 stories tall. The next tsunami, 40 seconds later, because it would be pulsed every 40 to 50 seconds, the next tsunami needs that water. There's not an unlimited supply of water. The first wave has got some of the water that the second tsunami wants to use. So what happens? The first tsunami goes in only as far, it goes 40 seconds into land. Then it's pulled, 20 seconds into land, 20 seconds back for the next tsunami. So in fact, if you do the calculation, you can show the tsunami would not go past about a quarter mile inland. You could set up a rope, you know, like one of those club ropes, and just sit there and just watch the whole thing happen. The waves come in, they pass through the multi-million dollar Malibu homes. The wave comes out, brings the home with it. Next wave comes, takes the home back in a slightly different shape than it was before. This process basically ablates the entire west coast of the United States. We would know this in advance, thanks to Isaac Newton and his 2 equations he developed as a 26-year-old virgin. And so, so actually nobody has to die. It'll still do the $10 trillion in damage, but nobody, we know this in advance.
He says, quote, "I think the major branches of discovery are behind us." Do you agree?
Of course not. Oh my gosh. That is, I would say this to the man's face. You can't be more, let me be polite. Previous statements such as that made by physicists of the past have proven to be extremely short-sighted. How's that for polite?
That'll do. That'll
okay, so there's a physicist, one of these Nobel Prize-winning physicists in the 1800s going into the 1900s, the turn of that century. We were at the top of classical physics. Newton's laws were working, electricity was understood. We had the power of knowledge of the laws of nature. And they said, but there are a couple of things, there's still some unknowns, but that's just a matter of getting an extra decimal place in the measurement. But we're done. We're done here. Just a few clouds on the horizon. We're good to go. Don't become a physicist. There's nothing left to discover. Right. And what would happen in the next 20 years? Relativity would be discovered, special relativity and general relativity, the expanding universe, quantum physics. All of classical physics would be turned on its ear because of the discoveries in the very 2 or 3 decades to follow the uttering of that statement. So, of course, he can't see the future. That's kind of what it means to not be in the future. Half of my library are old books because I like seeing how people thought about their world at their time so that I don't get big-headed about something we just discovered and I can be humble about where we might go next. Because you can see who got stuff right and most of the people who got stuff wrong. A healthy NASA is a healthy America. And the two, as NASA's future goes, so too does that of America. And if NASA's healthy, then you don't need a program to convince people that science and engineering is good to do, because they'll see it writ large on the paper. There'll be calls for engineers to help us go ice fishing on Europa, where there's an ocean of water that's been liquid for billions of years. We're going to dig through the soils of Mars and look for life. That'll get me the best biologists. Look at the NASA portfolio today. It's got biology, chemistry, physics, geology. It would be planetary geology, aerospace engineers, mechanical engineers, electrical engineers, all the STEM fields. Science, technology, engineering, and math represented in the NASA portfolio. A healthy NASA pumps that. A healthy NASA is a flywheel that society taps for innovations.